Welcome, NEET aspirants. In this video, we will explore two vital concepts: the angle of contact and the pressure inside drops and bubbles. Understanding the angle of contact can help explain why water beads on a waxed car surface but sprays out on a clean glass table. This knowledge is crucial in the field like surface chemistry and engineering for designing materials with specific weighting properties. Similarly, knowing about the pressure inside drops and bubbles can shed light on the stability of emulsion in food products, the behavior of bubbles in carbonated beverages, and the efficiency of microfluidic devices. These insights drive innovation in industries ranging from food and beverage to biomedical engineering. Understanding these principles is essential for your studies, particularly in biology and related fields. Let's dive in. Angle of contact is a fundamental concept in the study of fluid dynamics, especially in understanding the interaction between the liquids and solid surfaces. When a liquid meets a solid, its surface forms a curve at the point of contact. The angle between the tangent to the liquid surface at the contact point and the solid surface beneath it is termed as the angle of contact. This angle holds significant importance in various natural phenomena and practical application. For instance, it governs the behavior of liquids in capillary tubes, determine whether the liquid spreads or builds up on a surface, and influence the formation and stability of drops and bubbles. The angle of contact varies depending on the nature of both liquid and the solid involved. It can range from nearly 0 degrees, indicating the complete wetting, as seen with water on a clean glass surface, to close to 180 degrees, indicating non-wetting or super hydrophobic behavior, as observed with certain repellent coatings. Understanding the angle of contact is essential in the field such as material science, surface chemistry, biology, and engineering. It forms the basis for designing surface with specific wetting properties, developing the advanced coating, and optimizing the process like inkjet printing and microfluidics. Pressure difference across a liquid surface. Surface tension, the cohesive force acting on the molecules at the interface of a liquid, gives rise to a pressure difference across the surfaces. This pressure difference is crucial for maintaining the stability of the liquid surfaces, particularly in the formation and existence of drops and bubbles. If the free surface of a liquid is plane, then the surface tension acts horizontally. It has no component perpendicular to the horizontal surface. As a result, there is no pressure difference between the liquid side and vapor side. If the surface of the liquid is concave, then the resultant force are due to surface tension on a molecule on the surface act vertically upwards. To balance this, an excess of pressure at the concave side is necessary. On the other hand, if the surface is convex, the resultant force R acts downwards and there must be an excess of pressure on the concave side acting in upward direction. Thus, there is always an excess pressure on the concave side of a curved liquid surface over the pressure on its convex side due to the surface tension. However, in curved surfaces, such as drops or a bubble, surface tension causes an excess pressure inside compared to surrounding medium. This excess pressure ensures that the drops and the bubble maintain their shape by counteracting the inward forces trying to collapse them. The relationship between the excess pressure, surface tension, and the curvature is mathematically described, providing insight into the various phenomena like bubble formation, droplet coalescence, and stability of liquid films. Practical examples such as the soap bubbles or water droplets on the surface offers tangible demonstrations of these principles. Excess pressure refers to the pressure difference between the interior and exterior of a liquid drop or a bubble, which is necessary to maintain its stability against the surface tension forces. Without this pressure imbalance, drop would collapse into the bulk liquid and bubbles would dissolve. The excess pressure inside the drops and the bubbles is directly related to their curvature, with smaller drops or bubbles requiring higher pressure to resist collapse. This concept is quantitatively described by Laplace's law, which relates excess pressure to the surface tension and curvature. Imagine the drop to be divided into two equal half. Considering the equilibrium of the upper hemisphere of the drop, the upward force on the plane face ABCD due to excess pressure P is F is equal to P pi R square. Here excess pressure is the difference between the pressure inside minus pressure outside. If T is the surface tension of the liquid, the force due to surface tension acting downwards along the circumference of the circle ABCD is T into 2 pi r. At equilibrium, P pi r square equal to T into 2 pi r. Therefore, P is equal to 2T upon R. A soap bubble has two liquid surfaces in contact with air. One side the bubble and the other side of the bubble. Therefore, the forces due to the surface tension is equal to 2 times of 2 pi r into T. At equilibrium, P pi r square is equal to 2 into 2 times of pi r t. Therefore, P is equal to 40 upon R. Thus, the excess of pressure inside a drop is inversely proportional to its radius. The pressure needed to form a small bubble is high. This explains why one needs to blow hard to start a balloon growing. Once the balloon has grown, less air pressure is needed to make it expand more. In practical terms, excess pressure influences the various phenomena, including the behavior of bubbles in carbonated beverages, the stability of emulsion in food products, and the performance of microfluidic devices. Understanding and controlling the excess pressure are essential in designing different processes and the products in diverse industries from cosmetics to aerospace engineering. Overall, the concept of excess pressure provides valuable insight into the study and behavior of a liquid interference, offering a foundation for both scientific inquiry and technological innovation. Now, let's solve some numerical problems. I recommend visiting our website www.ginit.com to practice more need-based multiple choice questions. Problem 1. If a soap bubble expands, ask to find out whether the pressure inside the bubble increases, decreases, etc. From the formula 40 upon R. Here excess pressure is pressure inside the bubble minus pressure outside. Therefore, P inside is equal to P out plus 40 upon R. If the soap bubble expands, it means its R increases, therefore pressure decreases. Option 1 is correct. Problem 2. A soap bubble having a radius of 1 millimeter is blown from a detergent solution having the surface tension of 2.5 into 10 raised to minus 2 newtons per meter. the pressure inside the bubble equals at a point Z0 below the free surface of water in a container. It means we have to find the depth of point Z0. Now, excess pressure P equal to 40 upon R, and the gauge pressure at point Z0 is equal to rho G Z0. Now, external pressure on the soap bubble is P0, and the same pressure will be at a distance of Z0 below the free surface of water. Therefore, equation will become P0 plus 4T upon R is equal to P0 plus rho G Z0. We get Z0 is equal to 4T upon R rho G. On substituting the values of T, R, rho and G and simplifying it, we get it as 1 centimeter. Option 3 is correct. Before I, Avinash, sign off, I did like to ask you to share, like and subscribe to our channel. See you in the next video where we will dive into the fascinating topic of capillary action. Until then, keep enriching your knowledge and happy learning.